This presentation is on maximizing motor power at constant voltage. So speed of a motor depends on how much load there is on it. And we would call that load torque. So when a motor is loaded with no torque, it spins at a no load speed. So if you can imagine an electric motor just spinning, connected to a battery, nothing attached to the shaft that's turning, it's just spinning as freely as it can. That would be called omega naught or omega zero, and that's equal to the no load speed. When a motor is loaded with the stall torque, T stall, or this is actually tau stall, no more or more the motor will stop. And there we would say that tau stall equals the stall torque. So making sure that we have the symbols down here. This particular symbol is the Greek letter omega, lowercase, and this letter is the Greek letter tau. Okay, so tau is torque, omega is the no load speed. This omega is also the rotational speed, and this would have units of revolutions per second, radians per second, could be degrees per second. This is actually the SI unit, but this is probably the one here that we're going to use the most, revolutions per second. Where one revolution equals 360 degrees equals 2 pi radians. And then torque is a force applied times a distance, and that distance is going to be perpendicular to the force. This gives units of newtons times meters. When we look at a graph of speed versus torque, as we see here, we can see that it's linear with a negative slope. This value, the y-intercept, so y-intercept is the no load speed, or the omega naught. Down here, on the x-intercept, we have the stall torque. And we can see that whenever we have this, these graphed against one another, we have a linear plot, negative slope. So since this is a linear plot, we should be able to write a linear equation for it in the form y equals mx plus v. Y is the y variable, which is in this case is angular speed. M is the slope of our line, x is torque, and v is the y-intercept. So as we start to associate this equation for the line, the slope-intercept form with this particular line, what we find is that y is equal to speed, omega. That's going to be equal to a slope, and we can say that slope equals the rise, which here we have a rise from 0 up to omega 0. And that's going to be our rise divided by our run, which is going to be tau stall minus 0, so that's just tau stall. Multiplied by the x variable, which is tau, torque, plus a y-intercept. The y-intercept is omega 0. So here we would say that omega, this omega is an omega as a function of tau, as a function of this. So when tau has a certain value, this is the omega at that value. So we could say omega as a function of tau. Okay. Now we can look at the equation written out a little more neatly, and that is omega equals negative omega naught divided by tau stall times tau plus omega naught. And I did leave out my negative up here. This is obviously a negative slope, so we are going to have a negative slope on all of these speed versus torque plots. So this is our optional slide for you guys, the geniuses, and this is speed versus torque and its dependence upon voltage. What we can see here is that if we increase the voltage on the motor, then our this value is our no-load speed. A higher voltage is going to give us, in each case, from 3 to 5 to 7, and you can expect the same for 9 or whatever, volts to give us a higher no-load spin, no-load speed. We can also say that out here at the stall torque, that the stall torque is going to be higher as well. So when we look at this, one thing that we can always say is that our values are going to be higher for these endpoints on the line, and we need to keep that in mind if we are able to change our voltages. Most of our voltages are going to be consistent. But we can also, you can also imagine if you've got a motor spinning and you're trying to hold the shaft with your fingers, the lower the voltage, the easier it is that it's going to be to hold the shaft in place to keep it from spinning between your fingers. And that's because the stall torque is going to be way back here. There's also, when we're at a very low voltage, let's say somewhere between 3 and 0, somewhere in this range, we're probably going to have a point where when you connect the battery, the motor won't quite turn. At that point, we would say that the voltage supplied is not enough to turn the motor, but the reason for that is that there's friction within the motor that acts as a torque and keeps the motor from turning. So you're at the stall torque or below the stall torque for that particular voltage. So what we find is that basically, if you convert all this into some sort of statement, we can say that the motor speeds are going to increase. Speed versus torque depends on voltage. As we increase the voltage from 3 to 5 to 7, we find that the speed is going to increase for each of these. And these 120 and 90 and 60 would be angular speeds. All right, so our next equation deals with the concept of power. Power can get power from various functions, but the one that we're looking at here for the motor is that power is going to be equal to torque multiplied by angular velocity or angular speed. So when we look at this, first of all, I guess I should give you the units. The units of power is watts, which is equal to joules per second. So what this means, without looking at any of the equations to get there, is that if you multiply torque by angular speed, you're going to end up with joules over seconds. So just remember that power is in watts and watts is in joules per second, and that should be all that you need to know. Okay, so when we look at, back to the speed versus torque curve, we're going to say that, okay, at this point, as we analyze it, we have no power here. Remembering that power is equal to torque times speed. Why no power here? Well, the answer is pretty obvious. We're at 0 torque. Okay, so if we follow our x-axis, this value the y value for this, the x value for this is 0. And if we look down here, so if we have, let's come back to this, we have no torque. If torque is 0, then 0 times anything is still going to be 0. Down here, when we're at the stall torque, then we would say there's no power and y. If we're at the stall torque, then omega equals 0 because we're at 0 on the y-axis as we come across to here. So end result is that we've got, again, something that's 0 times some other value. Toss torque may be fairly large, but omega is 0 at the stall torque, so no movement, no power. Then at this point, we have the maximum power, and the question would become why. This value is the midpoint of the speed versus torque curve or line, and we would say that 1/2 of the stall torque is the torque that's going to give you the maximum power. So the midpoint of this curve. And the question would be why? Remember our equation here. So why half the stall torque? Well, if we take the former equation, the equation for the line from the last slide, and then we multiply both sides by torque. So we're just saying times torque, and then this whole side times torque. What we end up with on this side, torque times angular speed, is power, and then we're going to have to distribute this torque through the this tau through the rest of it. And what we end up with is that power is equal to a constant multiplied by tau squared plus an omega naught tau. What this is since we're in the form of a square here, this is a function that you would have covered in algebra, and it is a quadratic. And if we were to move, if we had, for instance, negative omega naught tau stall times tau squared plus omega naught tau minus power, I subtract this power over to this side, that's all going to be equal to 0. And you would have for your quadratic ax squared plus bx, and actually I'm minus here, minus c, and that equals 0. So we have our typical quadratic equation, or quadratic formula. Quadratic equation is what we would call this, I guess. This graphs as a down-facing parabola. All quadratics are going to graph as curves, and this would graph as a down-facing parabola, like so. So without all the algebra, if we can say that, okay, the algebra is going to take us to this graph, which is going to have this downward-facing parabola, then we can see that if we're going from no load here, where this is torque on this axis and this is power, if we've got torque 0 here versus stall torque out here, which is tau stall, then this point, the apex of the parabola, the highest point, is going to, or 1/2 tau stall, represents the point that gives us our maximum amount of power out here. So this would be P max. So if we want to maximize power, knowing the stall torque is rather important, because 1/2 of that value is going to give us the maximum power for our motor. So here we have, look at some of the robotics equipment. We've got a Vex motor here with a shaft attached to it running through a bracket, and someone is using a force probe here and lifting the bracket so that it jams against this this axle, this shaft, and the motor stalls. So what we would want to know is the stall torque. Okay, well, first of all, it's important to note that the way this is being done is we've got a shaft here, and then we're lifting up at 90 degrees. Okay, so this is going to give us a torque of we've got 1.4 pounds of force. Actually, this is probably already on the slide, so I'm just going to progress it. We've got 3-inch here, 3-inch beams or bracket, and then we've got a 1.4 pound force applied at 90 degrees to it. That gives us 4.2 pound-inches of torque. And so this is the actual torque. And since it's stalled, we're going to make the assumption that they lifted on this this beam until the motor stalled out, and at the point that it stalled out, we had these values. So, at what torque will the motor deliver the maximum power? Well, it's going to be 1/2 of the stall torque, 1/2 of 4.2, which is 2.1 pound-inches of torque. It's going to be the best value. So on this slide, VEX application, pick a gear ratio, we're taking the same motor from the previous slide, and we're using it to power a winch with a drum of radius 2 inches. So from the center of the drum to the outside edge of the drum where the string is attached. And that drum is lifting 0.2 pounds worth of weight down here. This would be a 0.2 pound mass. And we want to know what torque is the motor applying. Okay, so we've got torque out. Tau out is going to equal the distance times the force that is perpendicular to that distance. So if you think about this winch is essentially a wheel and axle. So we've got a 2-inch diameter to the or radius to the wheel. And we've got 0.2 pounds. That's going to be 0.4 pound-inches or inch-pounds, either way you want to put it, of torque. So suppose instead of a direct drive, just the shaft connected to the motor, we decided we wanted to use a gear ratio. What gear ratio would make the motor deliver the maximum power? Well, the gear ratio is going to be tau out is 0.4 inch-pounds, and tau in is 2.1 inch-pounds. Now this value right here is the torque that we calculated at 1/2 the stall torque earlier. So that 2.1 is there as the in, as the torque that's being put in by the motor, and the out is going to be on the winch itself. So that gives us a value, 0.4 divided by 2.1 is going to be 0.19. So I'm going to write that there because they did not, as the gear ratio. So to get that gear ratio of 0.19, we can use 12-tooth over 60-tooth gear ratio, or gears, 12-tooth gear to a 60-tooth gear. And so the gearing is the winch is geared so that the motor is delivering half its stall torque for maximum power. If we do that, you can see the gear ratio here. So we've got the 12-tooth gear here, and we've got the 60-tooth gear here. The motor is turning the 60-tooth gear. The 60-tooth gear is then turning the output gear with only 12 teeth. So that gives us an output over input gear ratio, 0.19.